Welcome to another podcast. In this episode, we're going to be taking a look at a class of differential equations called autonomous differential equations. The word autonomy means freedom in some sense, or self-direction. In this case, for a differential equation, it means that the differential equation is free from its independent variable. So when I talk about autonomous differential equations, I'll always be talking about things that look like, at least in the first order case, things that look like this. So notice that this differential equation is free from the t variable, at least explicitly. The t variable obviously is the independent variable in this problem, and y is a function of t, but nowhere on the right hand side does the t variable actually appear. This is sort of what you would consider to be autonomous in terms of a differential equation. Now, there's a couple of features of autonomous differential equations I want to go over with you, and then we're going to take a look at an example. The first feature is that y equals y naught is a critical point. If it makes the right-hand side 0. So critical points are points which make the right-hand side 0. We've seen this sort of thing before. This is akin to equilibrium points. In this case, y equal to y naught is always going to be a straight line solution. Not only is it going to be a straight line solution, but it's going to be a horizontal straight line solution, which means it's going to break the plane up into sort of these parallel regions. We're going to see an example of that here in a second. So if I have a critical point, that critical point is a straight line solution. And then finally, the last thing is all solutions are translations of one another. And what I mean by that is if you find one solution, all you have to do is horizontally shift the other solutions and it'll match up. And I'll show you when we graph it here in a second what I mean by that. Alright, let's look at a simple example to get started with here. I want to look at y prime equals y cubed minus y. And so the first thing you should do is solve for the critical points. So I'm going to set y cubed minus y equal to 0, in which case, do a little bit of algebra here. We'll get that y is 0, and we'll get that y is equal to plus or minus 1 as the critical points for this problem. Now the question is, what do you do with that? And so I have a couple of graphs that I want to take a look at, and I want to start with the graph in the bottom right corner. The graph in this corner is called the phase portrait, or the phase plane. It is the graph of y prime versus y. So the vertical axis is y prime, the horizontal axis is y, which essentially means I'm plotting the function f of y. So if I plot that function for this particular curve, it's going to pass through the point -1, 0, and 1. So let's draw this in. Alright, so there's the graph of y cubed minus y on the phase portrait. So understand that when you're looking at the y values on this graph, you're looking at derivative values for your solutions. What's important about this is we know exactly what the solutions are doing based off this curve. For example, because the graph of f of y is less than 0 to the left of -1, I know to the left of -1 my solutions are decreasing. I know because the graph in this region is positive, then in that region solutions are increasing. In this region, they're back to decreasing, and in this region, they are once again increasing. Now, because of that, that allows me to draw something called the phase line. And so you want to be aware that the phase line for a autonomous equation consists of basically reproducing this horizontal axis on a vertical line. So for example, my critical points are 0, so y equal to 0, y equal to 1, and y equal to -1. And the directions to the left of -1 we're decreasing, so we're decreasing below -1. We are increasing in here, we are decreasing in here, and once again we are increasing to the right of 1. So basically I just took this line right here and rotated it vertically, and that's what's called the phase line. So this is the phase line for this differential equation. Now, what does the phase line tell us? Well, it tells us some interesting behavior near the critical point. So for example, if I'm near the point 1, all the solutions are trying to get away from 1. You can see the arrows are pointing away from it. We call this particular behavior instability or unstable behavior. So this is an unstable critical point. Y equal to -1 for the same reasons is also an unstable critical point. And then y equal to 0, you see how the solutions are collapsing to y equal to 0. So we call that a stable critical point. Alright, so what if we wanted to sketch solutions? Well, because we know the critical points, we know we have some straight line solutions already. For example, if I start right here, I can draw in a straight line solution at the point y equal to 1. So this is the graph of y versus t. So I've got critical points at y equal to 1, y equal to 0, and at y equal to -1. Now, what are those points telling me? Well, because I know the behavior based off the phase line, I know, and I also know that all solutions are translations. That gives me a great deal of information about how to draw in a solution. For example, what if you're in this region? Well, if you're in between 0 and 1, then you have to be increasing. So if you look right here, in between, or excuse me, you have to be decreasing. In between 0 and 1, solutions are decreasing. You can't cross 0 and you can't cross 1. So the only possibility is you start off near 1, and as you go, you get closer to 0 asymptotically. Now, if all solutions are translations, then every other solution is going to behave similarly. It's just going to get shifted over. Between -1 and 0, all the solutions are increasing, and so increasing behavior that ends up near 0, increasing behavior, and you can see how the solutions are meeting at 0. Below -1, we're decreasing, we're getting away from the solution. And above 1, we're increasing, getting away from the straight line solution. So that tells me exactly what the solutions to this differential equation are going to look like. Now, I don't know their actual equations. We didn't try to solve for a general solution or anything like that, but I do know exactly what they're going to look like in the plane. And that's sort of the important application for us here in this unit. So there's a lot of new information that we went over. We went over what critical points are for autonomous equations, how to find them, what is a phase line, what is a phase portrait, and then how to plot the solutions based off that information. We also talked about stability types. So a lot of things to take into account here. We're going to have a couple more videos coming up about this topic, so please watch those and maybe give you a little bit more information into how autonomous equations work. Thank you for watching.